Val, to those of you who know what that is. So I want to start with 2 comments about this slide. So first, because it's a heavily AI audience, you may notice that here Batman is econ and Robin is AI. And the only reason is that the word econ doesn't appear in Robin's small symbol. So it's a completely logistical decision. I'm not trying to say anything about the relative importance of AI versus economics. And the second thing is you may notice the dissonance between my real affiliation and the bottom right hand of the template. That's because obviously I prepared the slide when I was the talk when I was in Harvard. So I tried to spend half an hour to replace this part with the CMU logo, and ultimately I decided to just tell you to ignore this part of the template. It's a much easier solution. Okay, so here's the theme of this talk, if it's not obvious from the title, that the interaction between AI and economics leads to new paradigms that can change the way we think about fundamental issues in AI and in economics. And I guess for many of you, that's not the first time you hear somebody talk about, like an AI guy talk about economics or about this intersection, but hopefully I'll give you some new ideas and maybe a new perspective about this interaction. So obviously we'll talk about AI and economics. In AI, I'll touch on a variety of subfields. I'll talk a bit about multi-agent systems, machine learning, planning, uncertainty in AI, and knowledge representation. Most of them I'll just give very brief examples of other people's work, and I'll go into a bit more detail about my work. And then on the econ side, I'll talk about 2 fields that I was more involved with, game theory and social choice theory. So the first part of the talk will deal with game theory and its interaction with artificial intelligence. So here's Robert Uman's definition for game theory. He's a Nobel laureate and a mathematician at Hebrew University. And he says that game theory is a sort of umbrella for the rational side of social science, where social is interpreted broadly. When he says broadly, it means it applies to people, but also to plants, to animals, and maybe one of the things we care about is computational agents. But really, I think the key word here is the word rational, which we'll come back to later. So obviously, there's been a long interaction between AI and game theory. Most of you are probably familiar with computer chess. This was one of the big goals of AI. I guess computer chess is not a lot about game theory and a lot more about AI, heuristics, algorithms, and also hardware to some extent. But more recently, there's work, for example, coming off Thomas Sandon's group here at CMU about computational poker, where poker is, in a sense, a more challenging game where you have uncertainty about the current state of the game, and that completely changes things compared to chess, for example. Or you have work coming out of Yoav Shoham's group in Stanford about computational pool, where one of the challenges is how to capture pool using new game theoretic models and how to use them to get good results in competitions. Okay, so obviously there's been this long interaction between AI and game theory, and what I want to ask is why is this interaction natural? Why is it important, and what does each side bring to the table? So game theory offers the principles of rationality. Game theory is about modeling rationality and modeling rational interaction in some sense. What does AI offer? Well, one thing AI offers is rational agents. And this is not as trivial as it sounds, because in human societies, it's well documented people are not rational. People do not behave in a rational way. And therefore, game theory doesn't work perfectly when it's being applied to a human society. Whereas in AI, if we think about a multi-agent system with these rational agents, the principles of game theory can actually work perfectly. So they can actually work better in a multi-agent system compared to a human society for which it was designed. Just to give you one example in the space, there's recent work about applying game theoretic thinking to planning, where you have a bunch of agents. Each one of them has a set of actions they can take and a cost for each action, and also his own goal and the utility for achieving the goal. And the question is, can we design plans that are immune to deviations by coalitions of strategic agents? In the sense that if a coalition decides to act on its own, it can design a better plan than the one that we're proposing. So that's work, for example, by Brafman and others. Another thing AI offers is a new way of thinking about rationality, thinking about settings where people, instead of having a fixed value for good, maybe can learn their value for good over time and can adapt. So for example, work coming out of David Parks's group in Harvard is thinking about these settings where agents are learning their values and trying to adapt the classic economic mechanisms to deal with this kind of setting. Okay, so I want to give you a more detailed example of my own work. And this example involves game theory and machine learning, or computational learning theory, if you will. And the question I want to ask is, what role do incentives play in the machine learning process? And how can we design machine learning algorithms that are immune to manipulation by strategic agents? And this is based on work with Ofer Deckel and Felix Fischer. Okay, so in this example, I actually want to take an unusual approach. I'll first give you the model, and then I'll give you the story, like some motivation, because it's, I mean, from experience, it's more confusing when I give the motivation before the model. So let's try to talk about the model, and I'll start with a very, very simplified version of the model that we deal with. So you have an input space, which I'll denote by X, and we have a bunch of players. Each player I controls an input point, xi, which is public knowledge. So everybody knows that player I controls this input point, xi. Now, in addition, each player has a label for his private input point, which I denote by yi, and this is private information. So only I know my label for the input point that I control. Now, in addition, we have a function class of functions that map the input space to real numbers. So essentially, they give a real label to every point in the input space. Now, the way this works is that each agent reports to me, I'm the center now, the designer. Each agent reports to me his label for his point, okay, which can be the real label, but it can also lie about this label. Nobody knows what the real label is except the agent, except the player. And now, given these reported labels, I have to choose a function from my function class. Okay, so I have to, in a sense, fit the data using a function from this restricted function class, capital F. Now, the players want the outcome of this process, want the function that I'm choosing to be as accurate as possible on their own input point. So each agent is looking to minimize the distance between the value of the function that I'm choosing and his label for the input point. And remember that my function class is restricted. It can be, for example, the class of linear functions. So I can't exactly fit the data. I'm not going to be accurate on some of these points. Now, as the designer, what I'm looking to do is minimize the overall error. I want to minimize the sum of distances between my function values and the labels given for these different points. So let me give you an example that will hopefully make this clearer. And by the way, if you have questions, feel free to stop me at any point. So in this example, the input space is going to be the x-axis. It's going to be
that criteria, norm 1 is intended?
Yeah. So I'm talking about the L1 loss function. It's just distance, Euclidean distances, L1. But some of our results also capture other norms as well.
Okay, so at this point,
at this point,
it's just notation of some distance.
Yeah, and for the purposes of the talk, it's just real numbers. So it's going to be just Euclidean distance on the real line. Okay. Okay, so here in this example, the input space is the x-axis. It's going to be the real line. The y-axis is the space of labels. Okay, so the position on the y-axis is the label. The position on the x-axis is the which point it is in the input space, and this is public knowledge. Okay, the x value is public knowledge. The y value is private knowledge. Now we're going to have 5 players. Each one of them has 1 point. And our function class is going to be the class of constant functions. So I have to fit the data with a function that has a constant y value. So the first question I want to ask is, what does the best fit, how does the best fit from the function class look like on this data? So it's going to be the function class whose y value is the median among these 5 labels. Okay, it's going to be this constant function. And the reason is that if I take any constant function that's higher up, let's say I'm moving from this point upwards, I'm going to get closer to a minority of labels and further away from a majority of labels by the same distance. And if I take any constant function that's lower, again, I would be getting closer to a minority and further away from a majority by the same distance. So because I want to minimize the sum of distances, this would be the optimal solution. So now, what I want to ask is, can a player get a better fit for himself by lying about his label? And to explore this question, let's look at player 4. If player 4 reports any label that's smaller than his real label, nothing would change because the best fit still goes through the median, which is in the same place. However, if player 4 reports a label that's higher than his real label, he can affect the outcome of this process. He can affect the best fit. His label can become the median label. But by doing this, he's only pushing the fit away from the real location of his label. Right? So he can affect the outcome, but only in a way that makes things for himself, things worse for himself. Okay, so more generally, we're going to say that the mechanism is strategy proof if a player can never benefit from misreporting his private information. And in our case, this means can never benefit from misreporting his label. And this is a very strong property. It has to hold even if I have full information regarding what everybody else is reporting and in any situation. Okay, so it's a very worst case assumption. Even if I know everything in any situation, I shouldn't be able to benefit from misreporting my label. And an even stronger property is called group strategy proofness, which means that even a coalition of agents cannot work together to benefit from misreporting their labels. Now, it's actually possible to show that in this setting, where each agent controls only one point, if your function class is convex, then taking the best fit is going to have this very strong property of being group strategy proof. Okay, if you just take the best fit, and this holds for any function class, for any convex function class, agents would not be able to benefit from lying. Now, in the case of constant functions, this is very easy to show and follows from known results. And the trick here is to show it for any function class that's convex. So it's a pretty general result. Okay, so let's make things a bit more complicated in terms of the setting. So I want to think about a similar model, but now instead of each player controlling one point, each player controls multiple points. So each player I is going to control the input points, xi1, xi2, and so on, multiple input points. And these input points are, again, public knowledge. And again, the agent, for each one of his input points, has a private label. Okay, so all the labels are, again, private. The identity of the input points is, again, public. Now, again, the players report their labels to the mechanism. And again, each player wants the outcome to be as accurate as possible, but now on all his points. So each player wants to minimize the sum of distances between the function values and his label for the points. And again, as a designer, I want the overall accuracy to be as accurate as possible. Okay, so I want to minimize the sum of distances with respect to all the points of all the players. So let's go back to a very similar example. So it's again the same thing. The input space is the x-axis, the real line. The y-axis is the labels, constant functions, same points as before. But now instead of having 5 players, we have only 2. Player 1 controls 3 points, and player 2 controls 2 points. Okay, so again, the global best fit, like before, is this constant function. The best fit from the point of view of player 1 for his 3 points is the constant function that goes through his median label among his 3 points. So for player 1, this would be the optimal, the ideal outcome for the process. And now again, I want to ask, can a player, let's say player 1, benefit by misreporting some of his labels? And you can see that here the answer is yes. Because if player 1 takes this point and says that the label is actually higher than it really is, he can actually drag the best fit along with him, and in particular drag it all the way to the point that's ideal for him. Okay, so by lying about one of his points, he got a fit that's more accurate with respect to his 3 real labels, this one, and this one. Okay, so we lose the strategy proofness property when we move to this setting with multiple points per player. So, the question is, what can we do in this setting? And there are multiple things that we can do. I want to give you one example. So one example is using a mechanism that we call project and fit. And it's a very intuitive mechanism. What I would do is for each player, I would take his labels and project them onto the best fit with respect to that player's data. Okay, so to project it onto the best fit that's ideal for that player. And then I would take these projected labels and compute the global best fit based on the projected labels. So I'll give you an example on the next slide, but let me mention that this mechanism would actually be strategy proof, would be immune to manipulation, and would give some quality guarantees with respect to some function classes. Okay, and let's see an example of how this works in the same setting. So here we said the optimal fit for player 1 is this constant function. So I take the labels of player 1 and project them on this function. Now, the best fit for player 2 is any constant function between this label and this label. So let's take this constant function. So I take the labels of player 2, project them on his individual best fit. And now I look at these 5 labels. Right? The median label here is at this point. So the global best fit on the projected label would be this red constant function. And this is what project and fit would return given the original reports, the original labels. Okay, so I want to finish the technical part of this example with almost the most general model that we talk about in the paper. So I'm still looking at L1 loss. This is for the purposes of the talk. But I'm going to look at a setting that's more learning theoretic with uncertainty and distributions. So now each player has a distribution over the input space, which reflects which part of the input space are more important to it and which parts are less. And each player also has a target function, which is the ideal labels for the points in the input space from its own point of view. Now, the way the game works is I sample the distributions of the different players. When I sample Carlos's distribution and get a point from there, I would ask Carlos, please give me a label for that point. Okay, so when I sample somebody's distribution, that player gives me the label for the point. And I get different points from these different distributions. Now, the players want to minimize the expected error with respect to their distribution and their target function. And as a designer, I want to minimize the expected error with respect to the average player. So I want to do as well as possible on average. And the point of this setting is that the results from the previous setting that I described, that had no uncertainty but multiple points per player, basically transfer over to this setting with uncertainty and distributions. So informally, basically for any accuracy epsilon and confidence delta, if you take enough samples, then a mechanism from the previous setting would give you the same results in this setting up to accuracy epsilon with probability 1 minus delta. Okay, so if you sample enough, basically this setting reduces to the previous setting we talked about with no uncertainty, but multiple points per player. Okay, so at last we reached the motivation for this work. And it's possible to actually motivate this work, I think, in many ways. The basic question is, just talking about incentives in a machine learning process. And initially we had in mind a search engine example. But I want to give you an even more, let's say, business-like, business-oriented example that's very real world. It's not a perfect fit with the model that I described, but very close, and has very strong incentives involved. So that's why I like it. And it involves a fashion company called ZARA, which is pretty unpopular in the US, but very popular in Europe. It's a Spanish fashion company. And the question is how to manage their inventory. Okay, so specifically they have a central warehouse somewhere in Spain. And the question is what quantity of each item should they send from the warehouse to each store around the world? So there's been a bit of work on this in operations research by Caro and Galien. And these guys designed a new process for inventory management for ZARA. So they came up with a regression learning process that takes as input historical data, but also reports from the store managers. So the store managers say, for each item, this is the quantity that they need. And then we have some process that's happening in the center and deciding about the quantities. Now, the issue here is that each store manager wants the quantity that he gets to be as close as possible to what he thinks he needs. Because if he gets more, he can't sell everything and it looks bad. if he gets less, he wouldn't be able to sell as much as he could have and wouldn't be able to look as good as he could have. And here the incentives are very powerful because store managers are compensated and promoted based on their sales performance. So they're really incentivized to do very well. Now, Caro and Galien actually say in their paper that ZARA's inventory distribution process, the one they came up with, could be further improved in the future by introducing explicit incentives for the stores to contribute accurate forecasts. Okay, so this is clearly an issue where you have this regression learning going on. You have very powerful incentives. And the question is, can we redesign this process according to the principles that I described before, perhaps, in a way that also eliminates the need for store managers to possibly lie about their predictions? Okay, so this is, I think, in general, I guess this talk is more theoretical than the average Robotics Institute seminar. And I think this is a great opportunity for collaboration because I'm talking about theoretical stuff which, should definitely be implemented, and that's the direction I'm moving in. So I'm definitely happy to collaborate with those of you who are interested about implementing this stuff. There are very, very big challenges and opportunities in this space, and I think specifically with this question. So I want to finish this part of the talk with sort of a more recreational slide, a more philosophical slide. Bear with me for a few minutes because I'm a pretty amateurish philosopher. So the question I want to ask is, we saw that there's this fundamental, maybe, connection between game theory and AI. But I want to ask even more than that, can I somehow argue that game theory enables AI on some fundamental level? And again, this is pretty philosophical and arguable, but I think makes interesting food for thought. So classic AI, and specifically, a lot of you guys, seek to design intelligent robots or agents. However, a lot of people in AI today, including many people in CMU, are looking instead of single agents at multi-agent systems, are looking at agent societies instead of single agents. Now, game theory, like I said before, tries to distill the principles of rationality. And here's the really arguable point, that rationality, it can be argued, is just another word for artificial intelligence. It's not how people actually behave, but it's how we perceive intelligent behavior. Okay, so it's sort of a sufficient condition for perceiving a behavior as being intelligent. Now, if you have a multi-agent system that's governed by the rules of game theory, the argument would say, it would be perceived by an outside observer as being intelligent, because we're perceiving rationality as being intelligent. And therefore, game theory can enable AI on the multi-agent level rather than on the more classic single-agent level. Okay, so, again, this is an arguable philosophical point, but I think makes for interesting food for thought. So are there any questions about this first part of the talk? Okay, so the second part of the talk is going to deal with social choice theory and its interaction with AI. So social choice theory is a theoretical framework for measuring individual interests, values, or welfares as an aggregate towards collective decision. And one way to sort of wrap your head around this is to think about voting, where you have a set of voters who have preferences over a set of candidates. The voters report their preferences, and then you have a voting rule that takes these preferences and chooses the social outcome, chooses the winner of the election. Okay, that's a special case of social choice. Now, the intersection of computer science and social choice is known by the unimaginative name computational social choice, and it's actually a field that grew inside AI and still largely lives inside AI. Okay, but it's become a pretty big subfield. And again, I want to ask, we have this interaction, but why is it natural? Why is it important? And what does each side bring to the table? So social choice theory offers very well-studied methods for preference aggregation. And one of the ideals of AI people working on social choice, or one of the big vision maybe, one of the ultimate goals, would be to use these very well-studied methods from social choice in order to reach consensus in multi-agent systems, to reach decisions in AI systems. And to give you an example, I have a recent paper in AIJ with Yanis Kargianis, where we look at cooperative multi-agent systems, and we show that using the tools of social choice theory, you can get outcomes that are also almost optimal in some setting, using very limited communication, so using a lot less communication than what you'd need otherwise, using tools from social choice theory. Okay, so definitely we can already see some applications of social choice in multi-agent systems, at least on the theoretical level. Now, what does AI offer? Well, AI offers complex preferences and ways of dealing with them. So, for example, there's work that's being done on voting on multi-attribute domains. So let's say you want to decide what to have for dinner, and you have to decide on an appetizer, a main course, and a dessert. Okay, so these are multiple issues. And let's say you have some voting rule where people say, this is what I want for each issue, for each course, and takes all of that and decides what to have for dinner for everybody. And the question is, can I take this big voting rule and decompose it into voting rules that apply to each attribute separately? Okay, so these are the kind of questions people are looking at, and they're closely related to stuff that's happening in the knowledge representation community. So in the social choice thing, I want to give you a more detailed example than before, and for this I'll need some, to give you a very, very brief crash course in social choice. So here are some of the, the real basics. So we have a set of voters that I denote by integers 1 to n. And an important point is that the voters here are going to be honest. So I'm not going to worry in this part of the talk about game theoretic considerations or voters manipulating the election. Everybody reports their real preferences. Now I have a set of candidates that I denote by letters. And each voter has a ranking over the candidates. So in this model of voting, each voter has a most preferred candidate, a second choice, a third choice, and so on, a full ranking of the candidates. Now, a preference profile is a collection of all the voters' rankings. So it's basically a vector of rankings, one ranking per voter. A voting rule is a function that takes as input a preference profile. So it takes as input the preferences of the voters. And given these preferences, it singles out the winner of the election. So it chooses a candidate given the preferences. So to give you some examples, one voting rule you all know from real life is called plurality, where each voter gives 1 point to his most preferred candidate, and the candidate with most points wins the election. Okay, so this is what you're probably all familiar with. A slightly more sophisticated voting rule is called Borda count, where each voter, if you have m candidates, gives m-1 points to the first place, m-2 points to the second, m-3 to the third, and so on down to 0. And again, the candidate with most points wins the election. Okay, but over the years, there have been many, many voting rules that have been proposed, some of them very, very sophisticated and clever. Now, the way social choice theorists compare different voting rules is using these axiomatic properties that one would intuitively want in a voting system. Okay? So they say, we have all these properties that we want. This voting rule satisfies this property, but not this property. And this voting rule satisfies this one, but not this one. And I want to give you one example of such a property. So it's a property called majority consistency. So if you're given a preference profile or given the preferences of the voters, a majority winner is a candidate that's ranked first by a majority of voters. And we say that the voting rule is majority consistent if, when it's given a preference profile with a majority winner, it would select that guy. So if we're given a preference profile where there is such a strong consensus candidate that's ranked first by a majority, that's the guy the voting rule would select. Now, I want to show you an example of Borda and the majority consistency. So this is a preference profile with 3 voters and 4 candidates. And for example, here, voter 1 ranks A first, B second, C third, and D fourth. Now let's apply Borda to this preference profile. So A would get 3 points from voter 1, 3 points from voter 2, and 0 points from voter 3. B would get 2 plus 2 plus 3, that's 7 points. And the other candidates would get even less. So B would be the winner in this preference profile according to Borda. However, in this preference profile, we actually have a majority winner who is candidate A. Right? Because candidate A is ranked first by 2 voters, which is a majority of voters in this example. So this example shows that Borda is not majority consistent. It's given a preference profile where there is a majority winner, but that's not the guy that is selected. And you can easily verify that plurality, for example, would be majority consistent. Okay, so like I said, I want to give you a more detailed example. And the starting point is thinking about this social choice setting that I just described. It's a very static setting in nature. Basically what you have is people reporting their preferences. And then we have this voting rule, which is basically a one-shot thing that takes the preferences, chooses a candidate, that's it. That's the end of the election. What I want to ask here is what happens if we're in a dynamic setting where voters can change their preferences over time? Okay, can we model such a setting, and what can we say about it? So this involves basically uncertainty in AI, decision-making under uncertainty with social choice, and it's based on joint work with David Parks from Harvard. So here I actually want to start with the motivation before giving you the model. And the motivation is going to come from these public policy advocacy groups. And to be concrete, I'll talk about a specific one called MOVEON.org. So MOVEON is obviously an online public policy advocacy group. It has 5 million members. So it has many, many people who participate. And basically what it does is advocate different causes, mostly democratic causes. So these guys are Democrats. They also have a handful of staffers, something like 12 people who work for MOVEON and are in charge of running the show, basically deciding which causes to advocate and how we're going to advocate these causes. Should we organize rallies or campaigns and so on? Now, ideally, the causes that we want to advocate should stem from the preferences of the MOVEON members. So in an ideal organization, the causes to be advocated should be decided directly by the members in the organization. Now, an interesting feature of MOVEON is that the time frames between deciding on advocating a cause and actually advocating it and organizing campaigns, rallies, and blah, 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 is very short. It's something like 3 weeks. Okay, so decisions are being made all the time. Now, the most interesting feature of this setting, I think, is that when you advocate a cause, you're actually affecting people's preferences regarding the relative importance of the different causes. You give them more information, you convince, and so on. And then 3 weeks later, after you've advocated the cause and you want to make a new decision, the preferences of your members are not the same as they were 3 weeks ago. So what's essentially happening is you're choosing a cause, you're choosing a candidate, if you will. The preferences of people are changing as a result of your choice. Then you're choosing another cause. People's preferences are changing, you're choosing another cause, and so on, every 3 weeks in this example. So it's an inherently dynamic setting where people's preferences are changing over time. Okay, and again, the question I want to ask is, how can we model this setting and how we can connect it to classic social choice theory? So to model the setting, we're using Markov decision processes. I know from Emma in her talk asked you guys how many of you know Markov decision processes. I think most of you did. But I don't want to go into the formal definition, so I'll try to sort of give the construct that we use through an example. So the basic component is transition models for the voters. So in this example, we're going to have only 2 candidates. Okay, the candidates are A and B. The possible states in the transition model are all the rankings over the candidates. So in this example, with 2 candidates A and B, the states are either A is ranked above B or B is ranked above A. That's the 2 possible states. Now, let's say that a voter has this transition model. Given that he's in this state, he ranks B above A, and now I choose to advocate candidate B, his preferences stochastically transition to a different state, to a different ranking. So for example, if I'm in this state, and candidate B is advocated, with probability 1/2, we would move to the other state. And with probability 1/2, we would remain in the same state. And if I choose candidate A to advocate, with probability 1/2, we would move to the, with probability 1, we would move to the other state. With probability 0, we would stay in the same state. Okay, so this is how you read these transition models. But basically the idea is, given the current preferences of the voters, I'm choosing a candidate, I'm choosing a cause to advocate, and this causes its preferences to stochastically transition according to these numbers. Now, in this example, I'm going to have 3 voters. 2 of them have this transition model. 1 of them has the other transition model, the one on the right. But crucially, the voters are assumed to transition independently. So the fact that these 2 have the same transition model doesn't mean they're always in the same state. All the transitions are independent. Okay, so the structure that we deal with is a bit more elaborate. We call it a social choice MDP. So it's a Markov decision process. The states of the social choice MDP are all the possible preference profiles. Okay, so each state gives you the ranking of each voter over the candidates. In this example, where we have 3 voters and 2 candidates, we have 8 possible preference profiles. So these are the 8 possible states. Now, the action space of this MDP is the set of candidates. So every time I'm in a state, every time I see this preference profile, I have to choose a candidate to advocate. So these are the possible actions that I can take. Now, the transitions in this MDP are derived from these individual transition models in the natural way. So for example, let's say we're in this state, and I take action A. And I want to know what's the probability of transitioning to this state. Okay, so again, I'm going to take the action A, and I want to compute the probability. So voter 1 has to go from BA to AB given the action A. So I'm looking at the transition model for voter 1, BA to AB given the action A. This happens with probability 1. Voter 2 has to go from AB to BA given the action A, and this again happens with probability 1. Voter 3 has to go from BA to AB given the action A, but he has a different transition model. So this happens with probability 1/2. So overall, my probability of going from here to here, given the action A, is 1 times 1 times 1/2. That's 1/2. Okay, so this is how I compute these transition probabilities based on these individual transition models. And in the same way, you can compute any of these transitions. So what I'm showing here is just the transitions for taking the action A in each state. But the complete illustration would also show you the probabilities for the action B. Okay, so we talked about 3 of the components of a Markov decision process. We talked about the state space, which is the space of preference profiles. We talked about the action space, which is the set of candidates. So we have to choose a candidate in each state. We talked about the transition functions, which are derived from the individual transition models. The last thing I have to tell you about is the reward function. So a reward function tells you for every state and every action that I take in that state, what's my reward going to be? Now, when I say I here, I am the designer, so I'm the center. I don't want to think about the reward of an individual voter. I want to think about the reward of a MOVEON staffer who's trying to control this whole process of people advocating and learning and so on. Okay, so I'm taking the point of view of the MOVEON staffer, if you think about the MOVEON example. So we're being very general about which reward functions we allow, but just to give you 2 very basic examples. One reward function could be that as the MOVEON staffer, I like candidate A. So in every state, when I choose candidate A, I get a reward of 1. Otherwise, I get a reward of 0. That could be a reward function. Another function, which I think is much nicer, is a social consensus reward function, where my goal as a MOVEON staffer is to steer society towards a state where there's a social consensus, because then advocacy becomes so much more powerful. So for example, if I manage to reach a state where there's a majority winner, a guy who's ranked first by a majority, and I choose that guy as my action, I get a reward of 1. Otherwise, I get a reward of 0. Okay, so here I'm getting rewarded by steering society towards states where there's a majority winner. Now, a policy in a Markov decision process selects an action, which in our case is an alternative, in every state, which in our case is a preference profile. And here's the point I want you to remember from this part of the talk, that the policy in a social choice MDP is a voting rule. It exactly corresponds to the definition of a voting rule that I gave earlier. It's a function that takes as input a preference profile, which is a state here, and outputs a candidate, which is an action in our case. Okay, so it's exactly a classic voting rule, and this is really the nice feature of this model that lets us connect it to classic social choice theory. And we'll see in a minute how. Okay, now my algorithmic goal is the standard one in the MDP literature. I want to maximize the infinite sum of discounted rewards. So I have some discount factor delta, and I get the reward for this round plus delta times the reward for next round, delta squared in 2 rounds, and so on. Okay, so that's not really crucial, but that's the standard goal. Okay, but this is really the crucial point. So I have this optimization problem. I'm giving the social choice MDP. I want to compute an optimal policy that optimizes my reward function. However, I have to do this subject to social choice constraints. Okay, the point is that the policy that I compute here, the optimal policy, is going to be a social decision-making mechanism. It's a function that tells me if these are the preferences of your MOVEON members, this is the cause that you have to advocate. So it's basically a social decision-making mechanism. And therefore, it has to be designed according to make sense from a social choice point of view. So for example, if my reward function is you get a reward of 1 if you choose candidate A and 0 otherwise, the optimal policy would always choose candidate A in every state. But that's not something that's sensible as a social decision-making policy. For example, if it's not majority consistent. If there's a majority winner, I may not select him because I always select candidate A no matter what. Okay? So my goal is to optimize the reward function, but in a way that the policy that I get, the result of this optimization process, satisfies given social choice axioms like majority consistency. So in general, finding an optimal policy in an MDP is easy, and there are tools to do it pretty efficiently. But here there are several obstacles that we have to overcome. So the first is that the state space of this problem is very large. It's going to be exponential in the number of voters and number of candidates. And to deal with this, we make 2 assumptions. The first is that we assume that the number of candidates n is constant. So in the MOVEON example, you may have 5 million voters, but you have only a handful of causes that you may want to advocate. The second thing is that we assume that the number of possible transition models is also constant. So you can have many, many voters, but we're sort of squeezing them into a number of relatively few transition models. Okay, so these are the assumptions that we're making. And given that you have these assumptions, you can get a relatively small state space by contracting symmetric states using techniques from AI from the 90s. So to see the intuition, let's go back to the social choice MDP that we saw before. Okay, so we had these 8 states, and we had the transition probabilities for taking the action A. Now I want to argue that these 2 brown states are symmetric, and these 2 gray states are symmetric intuitively. And the reason is that the only difference between these 2 brown states is that I've flipped the preferences of voters 1 and 2. But in our example, voters 1 and 2 had the same transition model. So in a sense, I don't care if it's voter 1 that has these preferences, voter 2 that has the other, or vice versa. Okay? Now, so let's look, for example, at the probability of, given the action A, going from here to this gray block. That would be 1/2. And the probability of staying inside the brown block is 1/2. And if I start from this state, the probability of going to the gray block is 1/2. And the probability of staying inside the brown block is 1/2. And that's not a coincidence, it's because of the symmetry. Okay? So what we do basically is, if you focus on these 4 states, contract every pair of states into one big state. And then, for example, if you start from the brown state, the probability given the action A of going to the big gray state is 1/2, and the probability of staying is 1/2. Now, the second obstacle that we have to overcome is that we want to compute an optimal policy subject to these social choice constraints. So there is some literature about computing optimal policies subject to constraints, but they have a very different structure. Okay, so we have to come up with custom techniques in order to deal with these constraints. So here's the type of results that we get, the theoretical results. If you assume, like I said, that we have a constant number of candidates and a constant number of transition models, then we can compute an optimal policy to the social choice MDP in polynomial time in the number of voters, where this policy is going to be subject to given social choice axioms. Okay, so it's going to be the optimal policy among all policies satisfying the axioms. And the axioms can be things like majority consistency that I talked about, ontoness, which I'll mention in a minute, and a variety of other things. Okay, so under the assumptions, this can be done in polynomial time. So to give you some idea of what's going on, I want to talk a bit about this ontoness property. Ontoness is just what you think. It means that the voting rule or the policy is onto the set of candidates. So for every candidate, there is some preference profile where that candidate is selected. So this is obviously a very, very basic, very, very basic property. Plugging it into the theorem is of intermediate complexity. So I want to sort of give you an idea how that's done. Okay, so what we're seeing here is the state space of the problem. Each hexagon is a state. And remember, a state is a preference profile. So each one of these hexagons gives you the preferences of all the voters over the candidates. Now, I grouped these hexagons according to symmetry blocks. So I didn't really formally define the symmetries, but intuitively, all of these states are symmetric, all of these are symmetric, and so on. Now, a policy here would label each one of the hexagons with the name of a candidate. Okay, so it's a mapping from states to candidates, so I would just label each one of these hexagons with a candidate. And an onto policy is a labeling such that the name of each candidate appears on one of these hexagons. Okay, each one of them has to appear somewhere. And for the example, I'm going to assume that I just have 3 candidates. So I just have A, B, and C. Now, ideally, here's what I would want to do in order to compute the optimal policy among all onto policies. So what I would do is I would select some state. I would select a symmetry block. I would select some state inside the block. They're all symmetric. And I would restrict it to A. So I would tell my policy, you have to choose A on this state. Now again, I would select a symmetry block, select a state inside the block, and tell my policy, you have to choose B here. And again, I would select a block, a state inside the block, and tell my policy, you have to choose C here. And now I would go to my magical MDP solving algorithm, and I would tell them, please compute an optimal policy subject to these restrictions. And from the algorithm, I would get an optimal policy where A is here, B is here, and C is here. Now, this policy is obviously optimal because I explicitly took the name of each candidate and put them on one of these hexagons. Now, the idea would be that I would repeat this process for every choice of 3 states up to symmetries. For each one of them, I would compute the optimal policy and its value, and I would take the best among all these policies. Okay, that's the idea. The problem here is that if I take a state and I restrict it to a specific action, I'm breaking the symmetries between this state and the rest of its block. Okay? So what I need to do is I need some procedure that would allow me to carve out a state out of its symmetry block and reshape the symmetries in a way that the state becomes its own block and in a way that the partition into symmetries isn't too fine. Otherwise, I would lose my efficient running time. Okay, so we do have such a procedure. I won't go into the details. But if you believe me, what we would do is we would choose a symmetry block, choose a state, and carve it out of the symmetry block and reshape the symmetry. So now I have new symmetry blocks, which are finer than before. And now among the new symmetry blocks, I choose one. I choose a state inside the block. I restrict it and carve it out. And then among the new blocks, I choose a block, a state, and carve it out. And I do this for every choice of 3 states up to these continually redefined symmetries. And I take the best thing. That gives me the optimal onto policy. Okay, so I want to finish this example with some of the challenges, and this is where you guys can come in. So first of all, this whole thing is assuming that we're given these transition models. So this whole model is based on the assumption that as the designer, I'm giving a model which tells me how the preferences of each voter are going to change. Now, these models, you can theoretically think of a variety of ways to come up with these models. One point I want to make is that even if you come up with very coarse models, so let's say you take your MOVEON members, you elicit a vector of features from each one, and then you match each vector of features with a transition model. Even if this model is very coarse, this still gives you a more principled way of making decisions than what's being done now. And over time, you can refine these transition models to give a better approximation of reality. Now, there is a question of whether these transition models actually exist. So there's a philosophical assumption here, in some sense, that people's preferences transition in a consistent way. that every time my preferences look like this, and this action is taken, my preferences would change according to the same distribution. So there are some big assumptions that are happening here, and there are very big challenges in testing them, both technically in terms of how we learn such transition models, and what's the right way to even think about it. Like, what kind of models can we even hope would exist? Now, a second challenge is coming up with practical heuristics. So I gave you some theoretical results that I think are interesting, but the polynomial time here is very, very bad. Like, the constants are really, really bad. And coming up with heuristics is really crucial in order to make this kind of thing work. And the final point I want to make about this example is that one thing I like about it is that usually computer science takes a very optimization-based approach. We're trying to optimize something. Social choice takes a very intuitive approach. It's sort of a very normative approach. So we have these properties that are intuitive, and we want to achieve them. And usually these two approaches are diverging. Usually they don't work together. And one nice thing about this example is that actually there's an interesting synergy between these two approaches, in the sense that we're trying to optimize something, but we're doing it subject to these intuitive social choice axioms. So it's a nice, a nice interaction between these two approaches. So some comments about computational social choice more generally. Classic social choice theory is full of impossibility results. Basically, a lot of the theorems say, if you want this list of properties in a voting rule, there is no such voting rule. You cannot achieve these properties together. Whereas computational social choice is very positive in nature. So basically, we're trying to use computational thinking, if you will, in order to get positive results and positive constructs in AI, but also in other environments. Now, the thing I think that I find most exciting these days is that AI is an amazing testbed for the principles of social choice. And the point is that in a human society, you're not free to choose the voting rule that you're using. Now, for example, there was a recent referendum in the UK about changing the voting rule, and all the academics agree that the alternative voting rule is much better than the one they're currently using. But the problem was that the alternative voting rule was perceived as helping Nick Clegg, who's this hated leader of the Liberal Democrats or whatever. So ultimately, the referendum was, the outcome was not in favor of changing the voting rule, although the alternative one is much better. So in politics, it's not just about the quality of the voting rule, it's about all these other political considerations. Whereas in a multi-agent system, when you're designing the system, you're free to choose any voting rule that you want. And I think even more exciting, in human computation environments, voting is being used all the time. Right? It's very natural because we have humans, they have to decide on stuff. People use voting all the time, but it's being done in a very naive way. And the question is, can we leverage all this knowledge from social choice theory in order to do voting in a clever way, in a more principled way in human computation systems? And the last point that I want to make is that when you think about this AI perspective of applying to multi-agent system, and again, this optimization perspective, the question is, do these social choice properties have an operational meaning when you have some objective goal? If you're trying to optimize something, is a property like a majority consistency, can we say that it's good in terms of optimizing our goal? Is there a formal way of saying this? Now, I think the answer should be yes, because intuitively what's happening in social choice is that people are trying to get a socially good outcome. Okay, so there is some implicit optimization going on. But I think saying formally something about this point is quite important, but also would require a conceptual breakthrough. Okay, so just to recap, our original theme was that the interaction between AI and economics leads to new paradigms that can change the way we think about fundamental issues in AI and economics. And we saw two, more detailed examples of this. One was when game theory, gives us a new perspective about machine learning, when we're trying to ask, can we design machine learning algorithms that are immune to manipulation? The other one was in the other direction, where stuff from AI gives us new models in social choice theory that have these dynamic preferences. Thank you.
Questions for Ariel? In this last result that you had, things were constant, that you mentioned as constant in the theorem, were those exponentials?
Yeah.
running time.
Yeah, so
So it's exponential the number of dynamical processes that you have.
Right. So basically, you get the running time would be you have a factor there that's n to the power of k factorial times n, where k is the number of transition models and n is the number of candidates. So it appears even with the factorial in the exponent. So I mean, so in theory it's polynomial time, but it's completely impractical, and that's why I'm saying, to implement these things, we really need completely different heuristics. Yep.
So now this, what you use is the assumption that the valid is secret from this assumption.
The preferences, you mean?
Yes.
Yeah. So definitely, in general, the assumption is that the preferences are secret, or private information, like we saw in the game theoretic setting. So often, a lot of the work that's being done in game theory says, is under the assumption that voters are honest. There is a big body of work at the intersection of game theory and social choice that basically asks the question: if the preferences are secret, and again, this worst case assumption, we have full information about what everybody else is doing, can we design a reasonable voting rule that's immune to manipulation? And the answer is no. So there's a theorem called the Gilbert-Satterthwaite theorem that basically says if you have at least 3 candidates and your voting rule can select at least 3 candidates, so let's say you have at least 3 candidates and your voting rule is onto, and it's not a dictatorship in the sense that there isn't one voter that always gets what he wants regardless of what everybody else is doing. If these things hold, then the voting rule has to be susceptible to manipulation. So basically, any minimally reasonable voting rule would not be immune to manipulation. And a lot of the really interesting stuff that's going on in computational social choice is asking how can we use computer science in order to circumvent this. So for example, manipulation can be possible in theory, but it may be a computationally difficult problem. So can we design a voting rule where on average it would be difficult for voters to manipulate, let's say in a cryptographic sense? Okay, that's one of the really hot questions in computational social choice. Emma. So you mean people are manipulating? So you say, yeah. Yeah. So that's actually a question I'm working on a related question right now. It's a good question. There is something tricky here in saying, you basically want to look at situations where you know how people. In order to analyze this, you have to know how people are going to manipulate. So you basically, you can look at situations where they have what's called a dominant strategy, which is for this group of people, this is obviously the best thing they can do. And then there are some preliminary results about saying the damage that can be caused is not this. But another related issue is saying, the Gilbert-Satterthwaite theorem tells us that for any reasonable voting rule, there will be situations where you can manipulate. But these situations can be rare or not so rare. So the question is, how frequent are these situations? And there's also quite a bit of work about that.
All right, let's thank Ariel again.
Thank you.